Alright, my name is David Strickland and I'm doing a reassessment of chapter 14.1. The problem I'm doing is 14.p.53 in the book. Problem says a hollow ball with a radius of 2 centimeters has a charge of -3 nanocoulombs spread uniformly over its surface. The center of the ball is at -3,0,0 centimeters. A point charge of 5 nanocoulombs is located at 4,0,0 centimeters. What is the electric field at location 0,6,0 centimeters? The two equations I'm going to be using is E net equals electric field 1 plus electric field 2 and the equation for a point charge. Alright, now first thing you have to do is find R hat. To do that, it's vector R over absolute value R. Vector R is going to be the point we're going to be observing from minus the point of origin. And for this, I'm actually doing the sphere first. So it would be 0, 0,06, 0 meters minus -0.03, 0,0 meters. This gives me an R vector of 0.03, 0.06, 0, and for absolute value R, you just get the it's the square root of 0.03 squared plus 0.06 squared, which is about 0.0671. Now you put both of these R's into this equation to get R hat, and R hat turns out to be 0.447, 0.894, 0. Once you have that, you plug all those R's into the equation for a point charge, as well as the Q given by the problem for the sphere. And it is 9 times 10 to the 9th, which is 1 over 4 pi epsilon naught, times -3 nanocoulombs over 0.0045 meters squared times R. Alright, once you do the equation, once you multiply that this times 1 over 4 pi epsilon naught, you get -5,996.387 times R hat, and then you get that the electric field is actually -2.7 times 10 to the third, -5.4 times 10 to the third, 0 newtons per coulomb. And both vectors, all the vectors are going to be negative because of the electric field. Now for the second electric field, for the point charge of 5 nanocoulombs, it's basically the same thing with R hat, except obviously different numbers. Same equation though. So what you do is you take the, to find R hat, you'd have to get the vector R, which would be the point we're measuring at minus the point of origin, and you'd get -0.04, 0.06, 0 meters, and then to find the absolute value R, it's just the square root of -0.04 squared, a meter squared, plus 0.06 meters squared. Well, you square them. I mean, they're in meters, yeah. So you square them. So the absolute value of R is 0.0721 approximately, and you plug all those R values and the 5 nanocoulombs into the equation for a point charge. And camera's giving me a little bit of trouble. You get 9 times 10 to the 9th times 5 nanocoulombs over 0.07 0.21 squared times the r hat value. Alright, and once you do that, you actually get that the E electric field is equal to negative 4.8 times 10 to the third, comma 7.2 times 10 to the third, comma 0 newtons per coulomb. Now the final thing you have to do is just add the two electric fields up to get E net. Alright, and once you do that, you would find, here's the equation right here. Once you do that, you would get negative 7.5 times 10 to the third, comma 1.8 times 10 to the third, comma 0 newtons per coulomb. So the electric field is actually going in, that direction, net direction. That has been my assessment for 14.1. I hope it was adequate.